Silakan dilanjut Pak Isan.
Okay, so now I can start. Thank you very much for your kind introduction. And 1 week ago, I talked about the measurement of water vapor by using GNSS ground network. And today I'm talking about something higher, lithosphere, ionosphere. And also not only the phenomena in the upper atmosphere, but I mainly talk about the phenomena on the surface of the Earth, lithosphere, for example, volcanic eruptions and earthquakes. So these two different spheres, ionosphere and lithosphere, are studied by two different groups. And so this is a kind of interdisciplinary study about the link between the two distant spheres of the Earth. Okay, so this. I skip the introduction of myself because this is the second time, and I briefly review the lecture 1 week ago. So we use GNSS, or it started as GPS by American satellite system. And I'm going to use the stations deployed in Japan mainly. And this is one of the stations near my university. And there are many of those nowadays. And its main purpose is to measure the movement of the stations by the event like earthquakes. For example, we can map the cluster deformation by this earthquake using this network. So that is the purpose this network was deployed. And because GNSS can do many different things, we can apply this network measuring the ionosphere as well as troposphere. So last week, I talked about, maybe I will change it to the laser pointer. Yeah. So last time I talked mainly about the tropospheric water vapor, and today I use GNSS to measure total electron content. This is a number of electrons in ionosphere. So there are two different layers, ionosphere and troposphere, and both causes the delay of microwave signals from satellites. And today I'm focused on the ionosphere. And as you know, ionosphere is made by the sun, solar radiation. So it exists mainly on the day side of the Earth. So the Earth is rotating. One cycle is 24 hours. And we have more electrons as day side and less electron at the night side. So if you map number of electrons on the world map, it looks like this. So it has a maximum directly beneath the sun. So it is 12 o'clock at this time zone. And for example, if we use the satellite that doesn't move with respect to the Earth, for example, this is one of the Japanese satellite called QZSS. And we have a geostationary satellite as one of the systems. Then we can monitor a fixed point in the sky continuously over 2 weeks. Oh no, this is 1 month. Oh no, this is just 15 days in 2020. So you see daily change. Sun rises, then the electron increases, and the sun goes down, and electron decreases. So it repeats daily changes. And sometimes there's some anomalous amplitude. And so they do not repeat exactly the same pattern. So it is disturbed by many different things. And so we can see many different phenomena, geophysical phenomena from ionosphere. And today I'm going to introduce some of those. First, I talk about explosion in the sun. So this has nothing to do with lithosphere. So this is a solar phenomena. And there is sometimes a hole, so empty region made by human activity. For example, the launch of a rocket. So this is also not related to lithosphere. So I will call it in situ phenomena. Phenomena that occurs within the ionosphere.
Explosion in the sun. Itu masuknya pada YouTube atau bagaimana? Ini Zoom.
Then I'm going to talk about lithospheric phenomena, for example, earthquakes. Earthquakes makes waves in the atmosphere and can disturb the ionosphere. Also, there's an explosion on the ground. For example, the volcanic eruption. This is lithospheric phenomena that may disturb the ionosphere. Also, I will briefly talk about something that may occur just before large earthquakes. So this is gonna be the last topic. Okay, so let's have a look one by one. Let's begin with easiest to understand. So this is conceptual change of TEC in one day. So it has a peak at noon. And we often see there's a sudden increase at a certain time in a day. And this occurs simultaneously all over the world. And this is a typical signature of the solar flare. Nowadays, you often see such a phenomena because 2025 is solar maximum. So the sun is very active right now. And this is one of the real record of such phenomena, 2003. So this is the peak of 2 cycles before because solar cycle is 11 years. So this is 22 years ago. So it is 2 cycles before. And there was a big explosion on the solar surface, and TC suddenly increased. So this is very clear. And this is a close-up, and it starts suddenly and becomes peak in maybe 5 minutes or 10 minutes. So what happened at that time? And it is an explosion on the surface of the sun, and we call them solar flare. And often upper atmosphere researchers call them CME. So this is coronal mass ejection. So a huge amount of particles have been released from the sun, and some of them may reach the Earth and causes some interesting phenomena. Okay, and at this time, because this is a very large one, and it appeared at the first page of the newspaper. So it says it may influence the performance of GNSS and may cause some problem in the navigation of the vehicles. Okay, so that's the first example, and that is a solar event. And next example, it's opposite. It's sudden decrease of TC. It also occurs very suddenly. So this is the second example. And I will show real data that occurred in Japan, southern Japan, like this. So let's see the change that occurred around 2 o'clock. So it is about 11 o'clock in the local time. And now you can see the TC has dropped to almost 1/2 suddenly. So something very strange occurred at this time. And this is 10:34 a.m. Japan Standard Time on February 9. So we know what happened on this day. It is a launch of a rocket. It's a huge rocket called H2A. It uses liquid hydrogen as fuel. So naturally, in its exhaust gas, there are a lot of water vapor because they let hydrogen connect with oxygen and making the water vapor molecules. And normally in the ionosphere, there are almost no water vapor. But if you bring huge amount of water vapor to lithosphere, something strange occurs. So this is, for example, H2O is coming from the rocket, and it will get positive charge from the oxygen ion. Then it will connect with electron. And so this is a typical chemical reaction that occur in the ionosphere. So as a consequence, electrons disappear when the rocket ascends. For example, you can see green is normal, and the blue is negative anomaly of the number of electrons. So this is the launch pad of the H-2A rocket. So it flew southward and penetrated ionosphere at this position. Then the number of electrons decreased at this particular point. And this is one of the station recorded sudden decrease. So it's almost halved after the launch time. So this chemical reaction occurs very, very quickly. Okay, and sometimes it occurs for not a rocket, but by the ICBM, intercontinental ballistic missiles. For example, there was such missile from Korea to the Pacific Ocean. So it flew above Japan, and we could see its trace as a negative change of the number of electrons. And these are the time series. So we can know that missile has flown along this red curve. It's an event in 2009. So it was a two-stage rocket, and first stage didn't reach the ionosphere, but the second stage penetrated the hole in the ionosphere. And so we could see this hole by observing GNSS station in the northwestern sky. Okay, so this is not so interesting from geophysical point of view, but might be interesting from another point of view because there was a similar incident in 1998, and the same thing occurred in 2009, and we could compare their power. So the decrease in 1998 was much less than in 1929. So this means there is a improvement of the rocket made in North Korea. So this is might be important information for some kind of people. So now I gather many past examples and plot the drop of vertical total electron content as a function of the original background vertical total electron content. So there is a positive relationship. If there are more electrons, then there are more drops. And the same type of rocket on this particular line. For example, H-2A rocket, I observed 3 different launches. Then they are on the same line. And this is these red squares are the ICBM from North Korea, the newer generation. And this is an old generation. So we can tell how powerful is a rocket or a missile by analyzing the GNSS data. And the data are open, so anyone can analyze. Okay, so the third example. So this is lithospheric phenomena. Now it is not an increase and not a decrease, but it's a sudden oscillation like this. and the oscillation, and this moves. And this is a real record in 2011 in Japan. And I will magnify the data around this vertical line. So now you can see there's a sudden increase and a decrease. We call this N-shaped disturbance because this looks like an alphabet of capital N. And this is a typical signature of an earthquake. So if there is an earthquake, acoustic wave is excited by the uplift of the ground and makes wave, and it propagates upward and reach the ionospheric F region in 10 minutes. And if you observe the total electron content from one station, then there is a irregular electron density in the ionosphere. Then you get the signature like this. It's an oscillation. And it moves in the sky because this is a wave. And its propagation speed is acoustic wave speed. And acoustic wave on the ground is only 300 meters per second. But because the temperature is very high in the 300 kilometer from the ground, it's much faster. It's about 1 kilometer per second. And that is an earthquake that occurred one day before the large magnitude 9 earthquake. And this is a newspaper. No, it's 2 days before the magnitude 9 earthquake. And now we interpret this earthquake as aftershock and foreshock. So this is a foreshock of the main earthquake on March 11. But at this time, people didn't think this is a foreshock of the magnitude 9 earthquake. So the newspaper says this released some cluster strain, and it reduced the possibility of the future earthquake because they didn't know this is a foreshock. So this is quite misleading news about this earthquake that occurred 2 days before. Okay, and that is an earthquake. And now it is an explosion, and strong explosion also disturbs the ionosphere. This is a station in Israel, and something occurred here. And if you have a closer look at the change in TC, you see a small disturbance about 10 minutes after this line. And what happened at this time? It is an explosion, artificial explosion that occurred as an accident in a warehouse in the park of Lebanon, Beirut city, Lebanon. So this was so huge, like a volcanic explosion, and disturbed the ionosphere. Okay, so now I'm going mainly talk about lithospheric events and ionospheric disturbance. volcanic eruption and earthquake. And volcanic eruption, I talk about two different types of eruptions: Brinian eruption and Vulcanian eruption. And for the earthquake, phenomena after the earthquake and before the earthquake. Okay, so again, we use ionospheric delay of microwave signals. And what will happen in the ionosphere after a volcanic eruption? A Vulcanian type eruption is a kind of explosion. So it makes a very strong acoustic wave. And after that, I'm going to talk about Brinian continuous eruption. And this occurs often in Indonesia. Okay, so volcano is very, say, it's an interesting from geophysical point of view, and also it is important to monitor them to mitigate the disaster. So we deploy GNSS stations around the volcano. That is to monitor the inflation of the volcano by the increase of the magma in the magma chamber. So we deploy GNSS stations, and we can use these stations to monitor the ionosphere. So, and I will show some example at first. The 2004 volcanic explosion in Japan. And we can tell the intensity of the explosion by these ionospheric signals. Okay, so this is a classification of the eruption. And I'm going to introduce this Vulcanian. This is a kind of short-term, big explosion. And Plinian eruption is long-lasting, so continuous. It continues hours and sometimes for days. And 2004 eruption of Asama volcano in Japan was a typical Vulcanian eruption. So it makes acoustic wave. So just like the earthquake, and makes irregularity in the ionospheric electron density, then it makes N-type, N-shaped disturbance in the delay. So this is, for example, we call this type 2 disturbance caused by volcanic eruption. So it is upward propagation of the acoustic wave. So this simulates the upward propagation of the wave, and it's a snapshot at 11 minutes and 12.5 minutes and 14 minutes after the generation of the wave. And this is a view from upper side. So it is north-south and east-west. And middle one is a cross-section. And now this is up-down and east-west. And this is another cross-section. So up-down and north-south. And in the north-south direction, there is some difference between the north and the south. And this is coming from the geomagnetic field. And you can see that the wavefront expands and both in the vertical and also horizontal. And there is some requirements for the period or frequency that can reach the ionosphere. So, for example, our voice has a very short period and high frequency. So such audible sound cannot reach the ionosphere because it is attenuated. And also, very long period wave cannot go to the ionosphere either because it is destroyed by the gravity. So, and then becomes an internal gravity wave instead of acoustic wave. So only a certain period of acoustic wave can reach the 300 kilometer without attenuation. And for the volcanic explosion, we typically see the period of 1 or 2 minutes. And for the Plinian eruption, we see typically 4 minutes period disturbance. So both are within this window. Okay, this is eruption of Mount Asama that occurred in 1783. So this is a very big one, but it occurred again in 2004, but it was not so large. So, there's almost no casualties. But that eruption, it is volcanic explosivity index 2. It changed the ionosphere. The volcano is here. And we use the stations here to observe the ionosphere at this point, because ionosphere is 300 kilometers above, so there is some difference in the position of the ground station and actually observe the ionosphere. So now you see very clear disturbance about 10 minutes after the eruption. So this is just like an earthquake. And we could see such disturbance for many past volcanic eruptions. And some are in Japan, and some are in Chile, and some are in Indonesia. So these are the examples. We observed something, but I think the Pinatubo and older one are not with GNSS, but by some other sensors. Only after year 2000, so these eruptions were observed using GNSS. Okay. Yeah, this is Shinmoe volcano, VI2 in 2011. This is just 1 month before the magnitude 9 earthquake. And this also made disturbance in the ionosphere. It is not so large, but it's clear. And I compare the disturbance from 5 different volcanic explosions in Japan. And they occur 10 or 12 minutes after explosion. And they are not much different in amplitude, but maybe this last one has the largest amplitude. So these are the position of the volcano. So last one has VI3. So I think that's why its signal is a bit stronger. And we can compare the amplitude in the TEC signal, and yellow is background vertical total electron content. So this is relative amplitude. So in percent, for example, there's 2% of disturbance relative to the background. So I think this relative amplitude is going to be a useful measure for the intensity of the explosion. For example, this eruption number 3 and 4 are the same volcano, and they also deploy the infrasound sensor, and they compare airwave amplitude intensity, and this is very consistent with the relative amplitude ratio between the two eruptions. So I think this ionospheric disturbance is something to complement airwave measurement. So it is very useful to discuss the intensity of the volcanic explosion. And also, you can compare this artificial explosion in Lebanon with volcanic natural explosions. These are the signals in Israel caused by the explosion in Lebanon. So they are the simulation results. And now you can say this explosion was similar to one of the Shinmoe volcano eruptions that occurred in 2011. So we can compare artificial event or natural event by using the same quantity, ionospheric disturbance. Okay, so that is about that is a story about the explosive volcanic eruption. So I talked about knowing the explosion intensity by ionospheric signals. Okay, so now we talk about larger volcanic eruptions. For example, 2021 in Japan and 2022 in Tonga. So I'm going to talk about atmospheric mode. Mode is a certain wave that has some fixed frequency or fixed period. In a laboratory, you can do this. This is a tube, and you fill the tube with water in halfway and make a sound. Then at a certain water level, there's a resonance between the sound from outside and the sound within this tube. And you can see you can hear a certain sound. The same occurs in the Earth. So this is ground. And this is a mesopause. This is boundary between the mesosphere and thermosphere, maybe. And also there's a fundamental mode and a few higher harmonics. And this atmospheric mode is excited by volcanic eruption. And this I have already found many past examples. And this makes a certain sound with a period of 4 minutes, and it will go further upward and disturb the ionosphere. And by this kind of eruption, we normally see a very beautiful harmonic oscillation, total electron content. And this lasts for tens of minutes or hours. And it is not exactly one frequency, but there are higher mode. So you see 3 or 4 different frequencies by analyzing the TEC signal. But the lowest frequency or longest period is about 4 minutes. So this is basic mode. Okay, let's see the example. This is an example by an submarine eruption of Fukutoku Okanova. It's a very long, complicated name, but this is a very big eruption in Japan. And it occurred on this day, and you see the TC oscillation continuing several hours only on this day, and not on the previous day, and not on the next day. And if you analyze the frequency, then you can see there are 4 different modes. 3.7 is fundamental mode, and these are the higher harmonics. And they are all atmospheric mode. Okay, so if you do not well understand what is the mode, then it is like a recorder. So in Japan, in elementary school, boys and girls carry this to the school and practice performing this recorder. So you can make different sound by plugging or closing some of the holes in the tube. So it is the atmosphere is just like a flute, and it is played by volcanic eruption. So it has several different frequencies. And that is example in the submarine eruption in Japan. And maybe you remember 3 years ago, there's a much stronger volcanic eruption occurred in South Pacific Ocean. H2HH stands for Funga Tonga Funga Hawaii eruption. Well, we just call them Tonga volcano. So this is a picture from the space. And atmospheric mode signal was very strong. But unlike the previous case, we could see only the 3.7 millihertz only. And there are many interesting features that we do not understand very well. Okay, so let's see the results. And this eruption was so strong that it excited not only the atmospheric mode, but also the mode in the solid Earth. Solid Earth also has many different modes. And this particular mode, 0s29 in the solid Earth has the same frequency as the atmospheric mode. So there is a resonance between the solid Earth and the atmosphere. So it continued 24 hours. This is seismogram record. And this is TC data by GPS, and this is by GLONASS. You can see very strange pattern of total electron content. So it has continuing oscillation for hours and hours, continuing until the end of this day. And now we see other constellation, for example, European Galileo and Chinese Beidou and the Japanese QCSS. All of those recorded the similar monochromatic oscillation of TEC. And I have never seen such a long-lasting oscillation of TEC. And this is a station at Tsuwaru, small island. And this is a one-day record. And you can see that it's occurring here and here. So I think it's a bit strange. Sometimes it is excited and sometimes it's stopped and started again. So there are many interesting but it's difficult to understand phenomena. And it is not uniform in space. There's a strong excitation of the atmospheric mode here. And this is a volcano. And also here. So not everywhere. So it is not a simple phenomena. And also it was excited here. So it seems to be related to the distance from the volcano. And maybe it's a resonance between the atmosphere and solid Earth. So the wavelengths of the solid Earth mode may be related to this interesting pattern. It was published in GJI maybe 2 years ago. No, last year. Okay. So there is an atmospheric mode and also a resonance with the solid Earth mode. So there are many interesting things. Okay, so there are the story about volcanic eruption. And next I talk about earthquakes. And first I talk about the co-seismic. Okay, now there are electrons in the upper atmosphere, and we observe them, and there's an earthquake. And the wave propagates upward to the space, almost the top of the atmosphere. So, and it is not simply the acoustic wave from the epicenter. So there's a cluster uplift. This makes atmospheric acoustic wave. And also there are surface wave associated with vertical movement of the surface. It also makes acoustic wave. Also, there are longer period internal gravity wave. They all go upward and disturb the ionosphere. Okay. An acoustic wave typically has a 4-minute period, and internal gravity wave has a longer period, 10 or 20 minutes. And the velocity is different. Direct acoustic wave propagates with sound speed in the upper atmosphere. It is nearly 1 kilometer per second. And this surface wave origin acoustic wave propagates in 4 kilometers per second. And the gravity wave is much slower. So there are 3 different velocity of the disturbance. And this radio wave origin surface wave propagates all over the world. So even if the earthquake occurred in Sumatra, this is the 2004 Sumatra Andaman earthquake, we could see the change in ionosphere propagated by 4 kilometers per hour per second from the southern Japan to the northern end of Japan. So it is global propagation. And acoustic wave, it is not global, but it's regional. And for the Indonesian earthquake, you can see the disturbance only within Indonesia. And Japanese earthquake, we mainly observe within Japan. So it looks like this. So this is the initial acoustic wave pulse. This amplitude reflects the magnitude of the earthquake. So larger earthquakes makes larger disturbance. So that is quite natural. And also there's some interesting atmospheric mode excited by earthquake. Okay, so this is my collection of coseismic disturbance in ionospheric total electron content by many different earthquakes. So 2004 Sumatra and Tohoku, Japan, and the Chilean earthquake. And this is a Sumatra earthquake in the Indian Ocean. And this is a Bengkulu earthquake. So many of the strong earthquake is in Indonesia. And also in Chile. So magnitude 9 earthquake makes the largest signature, and magnitude 7 makes a small signature. So it is a function of magnitude. So this is the amplitude. So this means if you observe the electron content change, then you can tell the magnitude of the earthquake. And you need to wait 10 minutes for the acoustic wave to travel from the ground to ionosphere, but you can determine the magnitude 10 minutes after the earthquake, immediately after you observe this signature. And this is very useful. For example, this is a case in the March 11 Tohoku Oki earthquake, and that occurred 8 to 10 minutes after the earthquake. And you see a very strong disturbance here. And this amplitude tells something about the magnitude. And this is very quick. I show you some confusion about the magnitude of this earthquake by using the seismometers. So this is immediately after the earthquake. The news said it's magnitude 7.9. So this is very much underestimated because they use the seismometer record and it is saturated easily. And the tsunami arrival time was announced about 4 or 5 minutes after the earthquake. and they issued the alert. And the first tsunami arrived 15 minutes after the earthquake. Then the magnitude was revised to 8.8 here, but this is still underestimated. And this is after the arrival of the tsunami. So if we can know the magnitude, exact magnitude 10 minutes after earthquake, it is quite useful for tsunami early warning. And the situation has now been improved, and I think this doesn't happen anymore by using many different ways. And also, if you determine the amplitude of the ionospheric disturbance, there is some problem, the directivity caused by geomagnetism. From the south side, it looks larger. And in the southern hemisphere, if you look at the earthquake from north, it becomes stronger. And that is caused by geomagnetism. For example, this is an earthquake in South America and Chile, southern hemisphere. And if you use a station north of the epicenter, it looks very big, but almost no signal in other directions. So you need to be very careful about this to enable the determination of the true amplitude. Yeah, that is because of the geomagnetic field. In the ionosphere, electron can move only along the geomagnetic field. So in the south side, it can move easily, but in the northern side, the particle motion is like this. So it is perpendicular to the geomagnetic field. So we see little signal. So that is caused by geomagnetic field. Okay, so that is a direct acoustic wave. Then I'm going to talk about this internal gravity wave. This is the third wave from the earthquake and also tsunami. This is very important for slow fault rupture. So you can tell if this earthquake is a slow earthquake by observing this internal gravity wave. Okay, so I already showed the relationship of the amplitude with magnitude for acoustic wave. And also there are different kind of wave, internal gravity wave. They have different relationship. It's much weaker. But for this particular earthquake, this one, magnitude is only 7.9 or 8, but internal gravity wave is very strong. This is Indonesian Mentawai earthquake. It's a tsunami earthquake. So the food can be classified into fast food and slow food. And earthquake is also the fast earthquake or just ordinary earthquake and a slow earthquake. So it occurs very slowly and it doesn't make a strong seismic wave, but it may cause a big tsunami. And they are called with many different names, after sleep, slow sleep event, very low frequency earthquake, non-volcanic tremor, or tsunami earthquake. And that occurs because of the special frictional property of the fold. There is a friction when it is stopping, and also another friction when it is moving, the called kinetic friction or static friction. So when it moves, at first static friction works, and then kinetic friction works. And in the case kinetic friction is smaller, then it's difficult to make it start moving. But after starting, it easily accelerate and become very fast. However, if the kinetic friction is much bigger, then it's easier to start, but it's difficult to accelerate. So the fold movement remains very slow. So this is a slow earthquake. And even if it is slow, so tsunami is a slower wave, and it can excite very strong tsunami. And in this paper, they compare 2009 Padang earthquake. This is a fast earthquake. And 2010 Mentawai earthquake. This is a slow earthquake. And this is a release of energy as a function of time. So Padang earthquake ended in 10 seconds, but Mentawai earthquake continued 2 minutes and slowly moved. And you can tell the difference by the acoustic wave. A fast earthquake makes a strong acoustic wave and less internal gravity wave. But tsunami earthquake, also it makes acoustic wave, but internal gravity wave is much stronger. So this is a slow earthquake signature in ionosphere. So Mentawai earthquake excited very large internal gravity wave because it is a slow earthquake. And this was published in 2022 in GRL. Okay, now the third topic of the earthquake. This is a very recent earthquake that occurred in Myanmar, in Southeast Asia. The problem in this country that there are many GNSS stations, but they are not active when this earthquake occurred. So there are stations, but they are all in different countries. So these are Chinese stations, and this is a station in Laos, and this is a station in Thailand, and this is a station in India, and also this is India. So no station nearby. So in this case, it is very difficult to map the fault slip because we do not measure the cluster deformation by using GNSS. However, if you analyze ionospheric disturbance, you can get some information about cluster deformation. So this is my ongoing research. For example, even if you do not have GNSS, you can use SAR, synthetic aperture radar, by using satellite. Then you can map the cluster deformation. Also, you can use the seismological data worldwide to map the slip. But they are both not direct, and still you need some additional information. For example, SAR is two-dimensional. It's very good in space. However, it is not good in time. So you can measure only once in a week or something like that. Okay, this is immediate release of the cluster deformation by using the INSA or synthetic aperture radar. This is from GSI in Japan. They mapped the movement of the crust. And also this is a data release from USGS. So they pinpoint some place where there are more displacement than other part. So they can show that the slip is not uniform, but no further information. And I'm going to use acoustic wave signal. And you can measure them in ionosphere. And now we do not use the amplitude, but we use the time after the earthquake, because this reflects the distance between the epicenter and the observing point. So this is just like determination of the epicenter of an earthquake by using seismometers. So you can find a similar figure in the textbook. And we are going to do that for Myanmar earthquake using the stations in India. So this is a signal. And we use two satellites, G14 and G22, so GPS satellite. So you think it's just smooth and there are no disturbance, and disturbance is very small. Okay, if you magnify and fit a polynomial, then you can see small departure from the smooth curve. And you see peak here, a small peak here, and another peak in the later time. So 3 peaks. So let's say 1, 2, 3. And they arrive at different times. So number 1 comes first, and number 3 comes second, and number 2 is the last. And by using this arrival time, we can tell where these acoustic waves were excited. And this is a typical surface uplift by a strike slip earthquake. If it is uniform, then you will see the uplift here and at the other end. And uplift causes a peak in the acoustic wave. So we are going to look for this uplifted region. And if there are patchy slips, then you will see many uplift centers along the fold. And if it is slowly, gradually decaying, then you see a large region of uplift. And this is a fold slip model by seismologists, not by geodesy. And they think there are a large slip in the northern portion and in the southern portion, and immediate slip, medium-sized slip in between. So there are 3 peaks of the slips, 1, 2, 3. So I think the 3 acoustic waves are coming from these 3 different slip patches. And they say earthquake record is not direct, and they want direct geodetic way of measurement. Okay, then use arrival time of the three peaks. For example, at one station, it observed two satellites, and satellite was observing the ionosphere at this star position. So the acoustic wave was excited along the fault, and as acoustic wave number 1, number 3, number 2, and arrived at the ionosphere at the different times. So this is a typical propagation of the acoustic wave from the epicenter, and the arrival time is a function of the distance. This is an empirical equation to get the distance from the travel time. I use this equation. And this is based on the acoustic wave velocity profile. And this velocity, about 0.95 kilometer per second. This is sound speed at 300 kilometer. It's the peak of the electron density. Okay, so by using this information, we can draw circles around this particular point. Then the intersection of the circle would be the place acoustic wave was generated. So I plot all the circles. Then you can pinpoint acoustic wave was excited here. And we repeat the same for the two other acoustic waves, acoustic wave number 2 and number 3. So now we can say acoustic wave number 1 was excited at the northern end of the fault, and acoustic wave 2 is in the southern part, and acoustic wave 3, this is small, and this is just in between. And we can reproduce the observed signature by this best fit acoustic wave source position. We could reproduce the curve. And we could also fit the curve by tuning the strength of the acoustic wave. The middle one is weak, and the first one and the second one are the large. So this corresponds to the acoustic wave 1 and 2 and 3. And this is comparing the fault slip and the source of the 3 acoustic wave centers. So yeah, we could know the cluster deformation by using ionosphere. Okay, so now this is the last topic. Maybe I finish this in 10 minutes. So this is a newspaper for the 2011 Tohoku earthquake. And you may expect, if there are any anomaly before the earthquake, to predict this earthquake. And there are many papers about that. And this is GNSS point near the coast. It is surrounded by the debris carried by tsunami. And now this station doesn't exist because this was much damaged by tsunami and was dismantled. And this paper shows anomaly in deformation. And maybe I have a chance to talk about this paper 1 week later, next week. And also some says, French group says there's an anomaly in the gravity. And this is a very short-term deformation just before this earthquake, again by a French group. So French group are very active in looking for precursors of earthquakes. Also, I will talk about this paper next week. And I say there is some anomaly in the sky. Okay, this is total electron content on the day of the earthquake. And earthquake occurred 5:45. And it is 2:45 in the local time in the afternoon. So I make it larger. And now you see many co-seismic disturbance here. And also you see some change before the earthquake. There's a change in trend. And if you add a reference curve, you see there are some positive anomaly before the earthquake. So this is, I think, related to the earthquake. This is introduced in many articles, and this is a popular science magazine in USA. And this is the English version, and also there are Japanese version and Chinese version. And also there's an article in Science Journal introducing my paper, Can Electric Signal in Earth's Atmosphere Predict Earthquakes? This is a USA Today newspaper article. They are all related to ionospheric change before earthquake. And this is one of the hypotheses why they occur. By laboratory experiment to destroy rock, it is known that positive electric charge are released and became mobile. They can travel to the surface of the Earth, and it makes some electric field before the start of the earthquake. And I can estimate how much electric charge may come from the depths and how much is electric field. Then it may reach the ionosphere and redistribute the ionospheric electron along the geomagnetic field. So I think this is what we are observing. And I wrote many papers already. And if you are interested, you can download some of those and read. And this is one of the recent one with Isan. And this is about the 3D tomography of the anomaly before the Tohoku earthquake. And also this is not a new earthquake, but the new data I got while I was in China in 2008 Wenchang earthquake. And this is, again, together with Indonesian people, it's a Turkish earthquake. Also shows a similar anomaly. And now I'm working on the 2025 Kamchatka earthquake that occurred in July. And we have one station here and observe the different satellites And this is earthquake time. And you can see very similar signal starting about 50 minutes before the earthquake, and slow increase of TC and recover after the earthquake, together with the co-seismic disturbances. So maybe we are writing a paper on this topic a few months later. Okay, so this is signature very close to the case in Tohoku earthquake in Japan. Okay, so now I summarize my talk by introducing some literatures: ionospheric seismology and volcanology. So this is most recent paper. It's about a recent earthquake in Japan in last year, January the 1st. So it showed a very clear atmospheric signal. And this is a review article in 2021, a few years ago. It's in a book published by AGU, American Geophysical Union. And one chapter is dedicated to ionospheric disturbances related to earthquakes. And this is available from my webpage. And there I compare many examples, past examples of TC change before large earthquakes. This is about one of the recent papers on the radio wave signal from the Turkey earthquake. We could observe very strong directivity of the radio wave. And this is also a review article that published this year. This is a book chapter in a book. And here I write about GNSS application for ionospheric seismology and volcanology. And this is very comprehensive. Okay, so I think this is last. Thank you very much for listening to our long talk. Yeah.
Thank you very much, Professor Heikki, for very interesting presentation, as always with cartoon and beautiful pictures. So I would like to continue today's talk with question and answer session. Please, anyone, if have question, comment, or anything, can just raise hand or directly talk to Professor Heikki.
Hello.
Okay, we have one questioner from on-site audience, please.
Thank you, Pak Isan. Thank you, Heikki, since it's very interesting presentation about earthquake and related to respond in ionosphere region. I want to clarify, after several study of earthquake and ionosphere, did Sensei find correlation between magnitude of earthquake and time precursor? I mean, if magnitude something, time that we can see from TEC or ionosphere parameter is something minute or minute before. Maybe CC have data that correlation between magnitude and time precursor. Thank you.
So I gave two different topic. The first one is to observe disturbance 10 minutes after the earthquake. Then we can tell from the amplitude of the disturbance exact moment magnitude of the earthquake. And that is not useful for earthquake prediction, but it is very useful for tsunami early warning. And the second topic is about the change in ionosphere before the earthquake. So that may be useful for the prediction of earthquake itself, including tsunami. And the second topic works only for very, very large earthquake, typically magnitude 9. So it is not still not so advanced to tell the magnitude from the change in ionosphere before the earthquake. So we are still just analyzing the relationship between the earthquake and its magnitude and the intensity of the anomaly before the earthquake. So I told about two different topics. So co-seismic and pre-seismic to make it clear. Okay.
Yes, thank you very much, Sensei. I think Sensei can also a little explain about the leading time of the pre-seismic in the ionosphere.
So I introduced mainly two examples. One is in the Tohoku earthquake, and in that case, it started about 40 minutes before the earthquake. So 40 minutes, maybe you may think long enough, but because it's just a change in trend. So before you notice the change in trend, it may require some time. So it could be 10 minutes, just 10 minutes before the earthquake that we notice some change has occurred. And for the case of the Kamchatka earthquake, it took us about 50 minutes before the earthquake. And it seems like that smaller earthquake has a shorter reading time. If it is magnitude 8, then it starts 10 minutes or 15 minutes before the earthquake. So it is extremely difficult to notice before the earthquake. But for the magnitude 9 earthquake, the signal is strong, and it occurs 30 or 40 or 50 minutes before the earthquake. So it could be useful.
Thank you very much, Budia and Profeki, for the question and answers. We have another comment. First, I would like to mention Professor Widodo in the chat of Zoom. Arigato, Professor Kasike. Enjoying your lecture, and he was one of the one who conducting survey after the tsunami in Mentawai 2010. So maybe I also have question regarding this slow earthquake typically triggering tsunami wave. How long the tsunami will come to the
that depends on the distance between the tsunami source and the nearby land area. So in the island, offshore the Sumatra Island, it is so quick. So tsunami early warning works only when the tsunami source is not so near from the land. And in the case of Tohoku earthquake, it took 20 minutes, 30 minutes after the earthquake. So tsunami early warning should work. And so it is a matter of the distance from the source and land. And Mentawai region is a very interesting region, and recently also there are smaller earthquakes. And we are also trying to detect some ionospheric signal, but we couldn't. It's not strong enough.
Okay, another question from chat on Zoom from Professor Erma. Thank you for your interesting talk. Do you found consistency in several other cases for the pre-seismic in the ionosphere as positive anomaly?
Oh, yes. The one of the special point in that phenomena is that there are almost no exception. So if you have a GNSS station at the right position and earthquake is large enough, then you see a similar signal 100%. So far there are no exception. Just one exception is 2005 March Nias earthquake. It was magnitude 8.7 or something like that, 8.5. It is large enough to disturb the ionosphere before the earthquake, but there was a strong plasma bubble activity at that time. So the TEC signal was very, very complicated, and we couldn't even see the co-seismic changes. So that is only one exception. In other cases, always we see the anomaly.
So thank you for your answer. It's very clear for me that have you suggestion for I think Indonesia for this I think implementation of the GNSS networking or receiving receiver in Indonesia, because it's I think that from your study it's very important for us to have receiving or proper of signal data from GNSS, because it's very useful and related useful related to catch up the signal. So have you suggestion as scientists for policy recommendation for maybe more implementation for GNSS networking in Indonesia? Professor Basuki, please. Yes.
Yeah, thank you for the question. For the tsunami early warning, I think it may become really practically useful by making a system of real-time measurement of TEC and at some stations near the coast, near the expected, for example, the large seismic gap you have in Sumatra, and 24 hours you can monitor the ionosphere, and data analysis is very easy, and you can get the real-time ionospheric signal. Then if it shows if there is an earthquake, then you have a look at the TEC signal, and by determining the amplitude, then you can tell if it is very dangerous and it may cause a huge tsunami. So I think it is already just a matter of implementation. And for the pre-seismic change in earthquake ionosphere, I think it is still just a research stage, and we need to understand the physical mechanism before the phenomena first, and establish the causal relationship between the faulting and the change in the ionosphere. And it's also for many different earthquakes with different magnitude. So it will become useful maybe 30 or 40 years later, not now.
Okay, thank you for your comment and suggestion.
Thank you, Prof. Herman, Prof. Eki, for interesting question and answers. Now, I think I will open a question from audience on site. Please open your mic, Bu Desi.
Oh, yeah.
Okay. So, Sensei, thank you very much for very interesting talk. So, actually, speaking of TEC, sometime I discuss with Isan also when he sometimes need the data for the TEC. So, I want to know more about the technical GNSS station. As you mentioned before, that in Myanmar they have less dense network, so it is difficult to monitor the ionospheric disturbance during the earthquake. So in Indonesia, we are now anticipating the many earthquakes. For example, in Siberut, Mentawai, as I mentioned before. We also anticipate the earthquake in Sunda Strait and the megatrust in the southern Java. So how, in your experience, how far or how close should we install the GNSS station for us to be able to monitor the disturbance in the ionosphere in case we have some earthquake in that megatrust area? So that's the first question. Can I ask the second one?
Yeah.
The second question is based on our experience in installing the GNSS station in Sumatra. We for now we only focus on the crustal deformation. So sometimes we limit our receiver only to track the satellite from GPS. So we don't trace the GLONASS or Galileo, etc. So how do you think can we improve the analysis or to detect the TEC change only if we have a GPS, or should we include the GLONASS and Galileo, for example, in our receiver tracking? And the third question is actually it's related to the Mentawai data we have before. So Isan sometimes Isan when we need the data, Isan always ask whether the earthquake occur during daytime or nighttime. So he says that and you also presented that it affects the number of electrons in the ionosphere. So is there any possible way that we can still detect the change of the TEC even if we have less electron in the ionosphere? So, or we just need to give up and stop searching because it has less TEC in the ionosphere? I think that's all of questions I have. Thank you very much, Sensei.
Okay. So in Indonesia, there are several different types of future earthquakes. Some are inland earthquake in the active fault, and others are the megathrust earthquake in the trench. So the TC change may occur by the inland earthquakes, but actually it is just for research purpose. And for tsunami early warning, I think it's only useful for offshore megathrust earthquakes, the magnitude 8 point something or more. So yeah, I think then to make it possible to use those stations for tsunami early warning, maybe you can deploy stations along the coast near the megathrust future earthquakes. I think that is the realistic way.
In terms of Sumatra, it's good enough because we have Mentawai for islands that we can install the stations. But in southern Java, we don't have that kind of island. So now we rely on the offshore island stations only.
Also, I think that we need some density of the stations. If there's an anomaly at one station and you are not sure if really occurs and just a local problem, or you can see the similar signature in the nearby station. So I think you need some density of the GNSS.
How dense would you suggest?
Maybe it just a few, at least a few stations covering rupture area of the future earthquake. So maybe one station in the 50 kilometer or 100 kilometer. And for the nowadays, there are not only GPS, but also many satellites. And I think it's a matter of the possibility that a certain satellite is in the right position.
Yeah.
So if you are lucky enough, just with GPS, you may see a very good signal. And that was the case in 2011. In Japan, we tracked only GPS, but still we could get a very good signal. So I think it's not essentially important to track every possible constellation. But if possible, tracking many satellites would be important. For example, I show the data in Kamchatka. That is only one station is alive, but that station tracked all the GPS, Galileo, GLONASS, and QGIS, BDS. So the number of observations was enough. And in Indonesia, there are several stations already. So even only with GPS, you could do some good works. And maybe online.
The last question, Sensei.
Oh.
If we have the earthquake on nighttime, is it still possible to?
Yeah, that is another problem. I didn't talk because ionospheric electron was much less during the night. So it is much easier to detect the anomaly. It occurs in the daytime. Yeah, that is the point I didn't talk today.
Okay, thank you, Bu Desi and Prof. Eki. Maybe we have actually very limited time, but maybe can Sensei quickly answering the question from the chat Zoom. First from Pak Sulaiman,
Tonga eruption.
about Tonga eruption.
So Tonga eruption, I introduced only the atmospheric mode signature. However, that is not all. It is known that Tonga eruption caused a special kind of atmospheric wave called ram wave, and it traveled around the Earth many times, and it can be detected by an array of barometer. And it made also another very interesting signal in ionosphere. And that is just like an earthquake, is an N-type wave, but with a much longer period. And there are many, many papers about that. And you can just look for a report. It is done also in Indonesia by Ethan, and also in China and worldwide. So you can find a paper about another kind of signal by the Tonga eruption. And the second one is the importance of atmospheric tidal dynamics. Atmospheric tide. Yeah, there is a daily repeating wind pattern in the upper atmosphere by atmospheric tide. And it also is a cause of the equatorial ionospheric equatorial ionization anomaly. So it is related to many important dynamics in ionosphere. However, for the very local phenomena like ionospheric disturbance by earthquakes and volcanic eruptions, I think tidal dynamics is a very large space phenomena, and it's not much relevant to the very local phenomena like earthquakes. Okay, and so another question? Oh.
Yeah, it's about strike slip fault triggering
Strike slip
CID.
fault. Oh yeah, that is a very interesting topic that I skipped. Atmospheric wave or acoustic wave was excited by vertical motion. So there are more vertical cluster movement by thrust earthquake or normal faulting earthquake, and less vertical movement by strike slip faulting. So the ionospheric signal by strike slip earthquakes are smaller than the deep slip earthquakes. But still we can see some signal, but it is smaller because it is a strike slip earthquake. It's just like a Myanmar earthquake of this year.
Last from
Okay.
Dr. Praitno regarding pre-seismic in TEC have been observed with other geophysical instrument like
Yeah, that is a
ionosphere.
very interesting question. So the GPS or GNSS has highest density in time and space, but also we have, for example, ion zone. There are maybe 5 or 6 working in Japan, and we could see some signal consistent with GNSS in the ion zone near Tokyo, just before the 2011 Tohoku earthquake. And in other regions, I have never heard of that. And also there's GNSS radio occultation measurement by using the lower orbiting satellite. And also there are many reports already published about the detection of the earthquake-related signal by using the GNSS radio occultation method. Yeah, I think they are. Also, there's a HF Doppler measurement of the ionospheric height change. So there are several different sensors, but they are not so dense in time and space as GNSS. Okay, and also another question, and how it stops after the earthquake. It just decays because during the build-up stage before the earthquake, there's a newly coming charge to the surface from the fault. But after the earthquake occurred, the stress was released. So there are no more new electric charge. So it just diffuses away. And anomaly in ionosphere will also decay. I think it's with the time scale of 10 minutes, 5 or 10 minutes. And we can see that in TC record after the earthquake.
Okay, Sensei, I would like to close the question and answer session.
Thank you very much.
Because we have limited time. Thank you very much, Professor Heki, for very nice talk. And I would like to let the audience give applause to Professor Heki. And maybe Sensei has concluding remarks.
Maybe the third lecture, the next week, is about the cluster deformation, mainly by earthquake. earthquake cycles, and so if you are interested in the solid Earth, then please attend next week. Thank you very much.
Thank you very much, Professor Kosakiheki, for very interesting talk. And I would like to conclude that today's talk is about ionospheric disturbance generated by lithospheric activity like volcano and earthquakes, including the rocket launch. And since I already reported some cases and found really interesting signatures in the ionospheres. And lastly, hopefully there will be further research and implementation of this research, as also raised by Professor Erma. So I think that's all also from me. Thank you very much for your kind attention and taking time to be here. I would like to return to MC Pak Mutar.
Okay. Thank you, Bapak Isan, for moderating for the presentation and discussion session. Excuse me, Prof, can you stop the share screen? Stop. Okay. Thank you also to Professor Kosakiheki for your presentation. Distinguished ladies and gentlemen, we finally come to the end of today's agenda. Let us close the webinar with photo session. Bapak Ibu yang hadir di Zoom, barangkali mohon izin untuk membuka kamera, kita akan melaksanakan foto bersama. Silakan foto di depan untuk yang di ruangan rapat. Oke, sambil di belakangnya. Silakan Bapak Ibu yang masih hadir untuk membuka kamera, kita akan laksanakan foto bersama. Saya akan ambil secara capture. Dan di sini juga di onset, di sini akan dilaksanakan foto menggunakan kamera. Siap. Oke. Yes. Oke. Kita sedang zoom. Lihat di kamera 3, 2, 1. Sekali lagi yang di zoom 3, 2, 1. Baik, terima kasih Bapak Ibu semua hadirin. Silakan. So the agendas we have presented to you all this day. Hopefully the information and from the presentation and discussion session will provide insight to all of us. Thank you very much for your attention. See you again at another Prima event. Wassalamualaikum warahmatullahi wabarakatuh. Have a good day.